Hi, everyone. Welcome to the first video on basic biostatistics for EBM. And so I'm going to share my screen and we can get started. Okay. Here's basically this is statistics review, and hopefully this will be all review for most of you, but if it's not, that's okay too. So our objectives today are going to be to understand the importance of biostatistics in medicine, explore key statistical concepts, and learn about types of data and appropriate methods. All right, so first let's get the definition out of the way here. Biostatistics is basically the application of statistical methods to health and medicine. Okay. Its role in medicine is to help you as a physician make informed decisions, drawing conclusions, and designing experiments. All right. So then the next question is, why biostatistics? Well, from an evidence-based medicine approach, this can help medical professionals make decisions based on scientific evidence. Okay, it also helps you in patient care, treatment effectiveness, patient outcomes, risk factors, and then probably on a grander scale, biostatistics is very important in terms of conducting research. Randomized clinical trials, retrospective studies, things like that. So here's some of the key concepts that we're going to cover in this particular video. We're going to first talk about the population and the sample and how those two differ. We will talk also contrast a little bit about descriptive statistics and inferential statistics. And we will also delve into measurement scales because understanding what kind of data you have goes a long way to helping you end up in the right spot. All right, so population versus sample. The population is basically the group that you're primarily interested in, okay? In a sampling standpoint, we might call that the frame, right? Or survey sampling. But so a sample is just basically the subset of the population. So what we're doing when we take a sample from a population is we're hoping to draw inference about the entire population by studying that one sample, if that sample was taken correctly. All right, descriptive versus inferential statistics. So a lot of times descriptive statistics are used just to describe what it is you have. Mean, median, standard error, standard deviation, range, interquartile range, all those sort of things are usually reported just to describe what your data set is looking like. Inferential statistics is actually using those descriptive statistics in such a way that you can draw conclusions about the population based upon the sample that you've taken. All right, now there are a lot of different ways that we can talk about data types. The one way that we can partition types of data into would be measurement data or categorical data. And then I've also put in parentheses the quantitative, qualitative, because those are sort of interchangeable terms there. All right, so if you're talking about quantitative data, keep in mind that the word quantity is sitting right there in the word, right? These are meaningfully numeric data. All right, so examples would include things that you can measure with a number, height, weight, blood pressure, things like that. Quantitative data can either be ratio or interval. Almost all the time it's ratio. And the difference between the ratio and interval is that the ratios make sense. So the way that I always look at ratio data is, does zero mean zero? If zero means zero, like number of children a family has, right? Zero means zero. Then the ratios make sense, right? When I have a family with 4 children, they have twice as many children as a family with 2 children. And you can build ratios on those. Strictly interval data does not work that way, but luckily we don't have a whole lot of examples of where interval data is um, actually utilized. The 2 examples that I can give are temperature and IQ. And there's a lot of others too, but those are the 2 that come immediately to mind. So when we say temperature, the when the weatherman comes on the local news and says, well, it was 30 yesterday, but it's 60 today. So it's twice as hot today as it was yesterday. Yeah, no, not really, because zero does not really mean zero there. Right? You can have negative 10 degrees Fahrenheit or Celsius. Right? Zero doesn't really mean anything meaningful on those scales. So temperature is one of those where there's not a ratio, not a ratio measure, at least not the temperature scales that we use. And then IQ is the same way. No one has a zero IQ. Zero doesn't really make any sense. They've scaled it to where the average is 100 with the standard deviation of 15. That's just a scale. Right? So that's someone that has a 200 IQ is not twice as smart as someone with a 100 IQ. It doesn't work that way. All right. So then on the other side, we have categorical data or qualitative data. And so I like to think of this as measurement scale. You're basically putting them in buckets. Right. So examples, things like anything that usually has anything to do with color, race, or blood type, things like that. Those, by the way, are what we call nominal variables. Nominal meaning basically they're just names and they have no relation to each other. Sometimes we have categorical data that is ordinal, though. And so anytime that you do a Likert scale kind of thing on a survey, that's ordinal. Those are still categories, but 1 is better than 2 and better than 3 is better than 4 or vice versa. All right. Also, if you're doing a survey and you ask for level of education or you ask for an income category, people rarely ever tell you what their income actually is, but they'll respond to a category. So those create categories that have order to them. And so when we exploit that ordinal nature, we can sometimes come up with different results. All right. A lot of times I get the question, how do I know what analysis needs to be used when? And that's a great question. I oversimplify that particular question I oversimplify the answer by looking at this 2x2 table here. This is not complete and this is not exhaustive, and there's certain nooks and crannies of this continuum that are not being spelled out here. But generally speaking, these are some good guidelines in what you how you make that call. So what I've got here in this table is I've got an explanatory variable across the top, response variables down the side. It really doesn't have to be an explanatory response kind of variable for all of these situations, but it does help to have these identified in this way. So if you look at a response variable, and a response variable would be the outcome of an experiment. So if we were looking at cholesterol, for instance, and looking at the effect that a drug has on lowering cholesterol, the cholesterol number would be the response variable to that. The explanatory variable would be the drug. So you give them a drug or a placebo or multiple drugs or however that works. And so depending upon whether the explanatory variable is categorical or numeric, and the response variable categorical and numeric, you get kind of this spectrum of four broad categories of analyses that you can look at here. And so the big ones for us are actually going to be the contingency tables, ANOVA and t-test, and regression correlation. Logistic regression is a little bit beyond the scope of anything that we would do here, though it's a very useful analytical technique. Right? So just as an example, if I want to compare two categorical variables, I'm going to probably want to use a contingency table on that. All right, which usually means we're going to do a chi-square test or a gamma statistic or something along those lines. If you have two numeric variables that you're wanting to compare, then you're looking at either a regression or correlation. If one of them was really a cause and effect thing, you could do a regression, but most of the time we're just looking at associations, which are just correlations. Right? And then the other one would be the t-test or ANOVA, where you're looking at a categorical treatment and then a numerical response. Okay? So here's an example. All right, so I asked a question here. Does fenugreek, garlic, or onion help in the treatment of diabetes, as according to Persian folklore? All right, so we're going to do an experiment where we have 4 treatments, the 3 mentioned above, plus control. And we're going to apply these compounds to rats and then measure their glucose levels. All right, so the important variables is the response variables, the rat glucose level. That one's meaningfully numeric. But the explanatory variable is the diet supplement. That's categorical. There was 4 levels. So if we look at our kind of our 2x2 table here, the numerical response and the categorical explanatory variable would lead us to doing an ANOVA in this particular case, where we would compare the 3 treatments and the placebo or control. Okay. All right. So that's certainly not an exhaustive look at basic biostatistics, but in our next video, what we're going to do is we're going to talk about hypothesis testing, concept of p-values, and we're going to fold all that into a little bit of talk about the scientific method. Okay. Okay. See you in the next video. Be well.